All right, this video is going to start chapter 14, and this is going all the way back to acids and bases. So the first part of this chapter is just kind of reviewing some of the stuff that you guys learned in honors chemistry about acids and bases. So let's just start with the Arrhenius model. Well, first of all, let me just go over acids and bases in general. Acids, just in general, fitting all of the different molds, are going to be something that increases the concentration of H plus in the solution. So it's something that causes the solution to have more H plus ions floating around, and that will change the pH. Bases are the things that decrease it. And there's two ways that they can do it. Well, actually just one. It's going to be something that bonds to the H plus so that it's no longer in the solution. So notice that our first kind of acid-base reaction here, the Arrhenius model, acids are producing the hydrogen ions. In this case, it's a very specific kind of base though. So this is going to be when base produces hydroxide. And so what happens is that hydroxide will bond to the H plus and form water. And so now you wouldn't have as much H plus in the solution. So it's not that the base is necessarily the hydroxide, it's that it's taking the H plus out of the solution. There are 6 strong acids right here, so you need to be very familiar with these. Make sure you put those on an index card somewhere or a sticky note. You're going to need to know off the top of your head which one of these are strong and which are weak. And the good news is that if it's not one of these 6, then it's a weak acid. So you only have to know those 6. For the Arrhenius model, it's, like I said, it's a specific kind of acid-base reaction where the base has the hydroxide. And what's going to happen is that you get water, and then you also get whatever's left over from the acid and base. Notice that we call it a salt, but keep in mind that it's not necessarily NaCl. It's not necessarily table salt. In chemistry, any ionic compound, we call that a salt. And like I said, the Arrhenius is limited, so it only applies to bases that have hydroxide. So the Bronsted-Lowry model is a better model because it's showing the transfer of the hydrogen, and the base does not have to be the hydroxide. So the base is going to receive the H+. It could be hydroxide, but it doesn't have to be. And so what's going to happen is that you have a transfer of the H+ from the acid to the base. So notice that the arrow is going from the acid to the base. On the other side of the arrow, you have the conjugates. So conjugates means what's formed after the hydrogen is transferred, the hydrogen ion. And notice that they switch. So if it was an acid, the HCl was an acid, once it loses the hydrogen, it becomes a base because now it's ready to receive a hydrogen. And the opposite happens with the base. It was a base, now it has an extra hydrogen, an extra H+ that it's ready to donate. So it becomes an acid. So whatever it was on the left, after it switches the hydrogen, it becomes the opposite thing. There's a couple of things about H3O+. First of all, it's called a hydronium ion, in case you see that in the writing anywhere. And I think this is later on in the notes on this page, but H+ and H3O+ are interchangeable. And that's because H+ is almost always going to stick to whatever water is around, and there's always water around. But the water is a liquid, and so it doesn't affect equilibrium and it doesn't affect the reaction. So you can either leave off the water and just write H+, or you can include the water and write H3O+, but in the world of chemistry they are interchangeable. So conjugate acid pairs, acid-base pairs, like I said, are what happens after the H+ is transferred, and it's kind of a competition. So I have that underlined down here. It's a competition between the two bases for the H+. So whichever base is a stronger base is going to receive the H+. And so you can see in this example right here, you've got water as the base, and over here chlorine, the chlorine ion is the base. So they're both pulling on this extra H+ right here, and it just depends on which one is the stronger base as to which one is going to receive the H+. All right, we are now going to start to apply some of our equilibrium topics to acids and bases. So first of all, just as a reminder, remember K equilibrium is the products over the reactants raised to the power of their coefficients. You do not include solids, you do not include liquids, but you do include AQ and you do include gases. So now what we can do is write out a general acid reaction. So we have hydrogen bonded to whatever acid it is. And the whole point of an acid is that it's going to break off H+, and then you'll have whatever you have left over with the negative sign. or down 1 charge. So when you take off the H plus, keep in mind that the charge goes down 1. If the original acid was already like +2, then when you take off the H plus, it will become just +1. So now we can write the K equation for this reaction. So now we can write that K is equal to H plus concentration times A minus concentration, the products, over the reactants. And that's where they're getting this. And again, you can use H3O plus if you'd rather. This is actually in your reference packet, so you don't even have to figure it out, although you can. It's not too hard to figure it out. But this is showing you how acids break apart. And we usually put a little A down here to show that it's for acids. Notice that water is not included in this reaction, even though you could write it. You could write that this is plus H2O liquid right here. But remember, we don't include liquids in the equilibrium expressions. But we do have to have water. It does play an important role because it causes the acid to break apart and ionize. So if you didn't have the water, then it wouldn't do its job. Can now use, so this is just an example right here. I was going to scroll down, but let's just do this example. So you can see that K is equal to the concentration of H plus times the concentration of Cl minus divided by the concentration of HCl. So now we can talk about K in terms of strength of an acid. So first of all, just as a reminder, if we have HCl breaking apart, HCl is a strong acid, we would have like 99 point something % is going to be ions, because this is a strong acid. And the definition of strong is that it produces a lot of H plus, meaning that it breaks apart pretty much completely. If we had a weak acid, some of it will break apart into ions, but like 99% of it will stay together as the HF. So again, strong acids break apart completely, weak acids mostly stay together and just break apart a little. So if we go back to our K equation up here, if strong acids break apart completely, you're going to have a whole lot of ions and just a few particles down here that are HA, which means that Ka is going to be very big. And the opposite will happen for a weak acid. So for a weak acid, remember 99% of it is the acid put together, and so you have a really big acid on the bottom, and so Ka would be small. So now what we can do is relate Ka to the strength of the acid. So Ka is directly related to acid strength. The bigger the K value, the stronger the acid. However, we do not have, this is important, a lot of people miss this, we do not have values of Ka for strong acids, because strong acids break apart so much that we just have such little amounts of this acid that it's really uncertain. And so we just know that Ka is really, really, really big, but we don't have a K value for it. We just assume 100%. This is why this is important. In a lot of your problems for this chapter, you're going to get questions where you think you might have to set up an icebox to figure out something, and you need the K value, and you're going to look at it and say, well, there's not enough information. They didn't give me the K for this acid. How am I going to set up an icebox for it? Icebox problems are only for weak acids because they're trying to figure out how much they dissociate. But you don't have to do that for strong acids because you already know that they're 100% dissociated. So you can just assume 100% dissociation. You can assume you have complete ions and none of the acid together, and you don't need a K value. In fact, you won't ever get a K value for a strong acid. So just keep that in mind. If you're looking for a K and you're trying to figure out what's going on, check if the acid that you're looking for is a strong acid, and if that's the case, then you don't need the K value. Weak acids are when equilibrium lies far to the left. So like I said, most of it is going to stay together as the acid. And this is important too. Weak acids are going to yield stronger conjugate bases. So sometimes they'll give you various acids and ask you to rank them in order of how strong they are, and they'll tell you how strong the conjugate bases are. So you can use that to help you figure it out. There's a little bit of vocab down here. You can probably figure it out. Protic means proton, and H plus is just one proton, because hydrogen most hydrogen atoms don't have any neutrons because they have a mass of 1 and an atomic number of 1. There are some on the sun. There's tritium and deuterium that have have neutrons, but most hydrogen atoms don't have any neutrons. And then if you take away the electron to make it positive, all you're left with is a proton. So H plus is the same thing as just 1 proton. So when they say protic, they're referring to how many H pluses they have. So monoprotic would be an acid that can donate 1 H plus, like HCl. Diprotic would be something like H2SO4. And it's not always how many hydrogens they have. So like acetic acid is looks like this. So notice that it has 4 hydrogens, but sometimes we write it so that this first hydrogen is over here by the side to show that that's the only one that will get ionized. So the C2H3O2 is a polyatomic ion. It's going to stick together, and those other 3 hydrogens are not going to break off. So this one is monoprotic, even though it has 4 hydrogens. Oxyacids are when the acidic proton is attached to an oxygen. And there's just a few more things, like organic acids usually contain COOH, which looks like this. And that's the hydrogen that can break off. Another vocab word, amphi, means both. Like amphibian can live in both water and land. And so water is amphoteric because it can act like an acid or a base. So it can act like an acid if it donates one of its hydrogens. It can act like a base if it receives a hydrogen. And we can write the reaction for that and write out the K expression, which is Kw. So if we talk about water breaking apart to form H plus and OH minus, and water is a liquid, then we can write the K expression for it. There are no reactants because water is a liquid, so all you have is just H plus times the concentration of OH minus. There's no coefficients, so you don't have to raise them to any powers. It's just the products multiplied by each other. These are always going to equal, in water, the same thing. So Kw is given to you as 1 times 10 to the negative 14th. This is in your reference packet. And it's just the concentration of hydrogen times the concentration of hydroxide. So if you ever have one of the concentrations, you can always find the other one. If it's neutral, these two concentrations will be the same. If it's acidic, you're going to have more of the H+, and if it's basic, you'll have more of the hydroxide. And notice that it doesn't matter what it contains, but the product of H+ and OH- will always equal this right here. So that's a constant. And the last thing for this lesson is the pH scale. So this is a scale that goes in general from 0 to 14. It can go just a little bit beyond the scale, so don't worry if you get something like negative 0.1 or something. But in general, we usually stay between 0 and 14. And you can figure out the pH from the concentration of H+ by using this equation right here. So pH is equal to the negative log of the bracket H+. And it would be helpful if you can rearrange this. So this one is given to you in your reference packet, but sometimes you'll have to go backwards. So just as a reminder that if you need the concentration of H+, it's equal to 10 to the negative pH. Those two equations are the same equation, they're just rearranged, depending on what you need. And there is something really, really weird about pH is the sig figs. So you have to be careful because for concentration, notice that in this number right here, we have 2 sig figs. That's not the same number of sig figs as pH. For pH, what you do is you take those sig figs and you transfer that to decimal places after the decimal. So however many significant figures you have, that's how many digits you're going to have after the decimal for pH. And there are no units for pH. So K and pH, I think, are the only 2 things in this class that won't have a unit. You can also do both of these for POH. So notice that POH is equal to the negative log of the bracket OH-. Again, you can put this here to remind you that you can rearrange that as bracket OH- is equal to 10 to the negative POH. And you can see the scale. So the farther you get from 7, the stronger it's going to be. So stronger bases or really concentrated bases would be close to 14, and then stronger acids are going to be closer to 0. Also keep in mind this is a log scale. So every time you move one place on this, you change it by a factor of 10. So if we're talking about a pH of 2 versus 3, 2 is 10 times more acidic than 3. 1 would be another 10 times, which would be 100 times more acidic than 3. 0 would be 1,000 times more acidic than 3. So every time you move 1, you just add another 0. And that is it for this lesson. Make sure you read the advice on page 669, and we're going to do some more acids and bases tomorrow.